Hello, everyone. Sorry about the hiccups. Good morning and welcome once again to the Friday JKMRC seminar series. On behalf of the University of Queensland and the Sustainable Minerals Institute, we would like to acknowledge the traditional owners and custodians of the land on which we meet today. We pay our respect to the ancestors and their descendants who continue cultural and spiritual connections with country and recognize their valuable contributions to Australia and the global society. It's my great pleasure today to welcome Professor Roussos, Dimitrakopoulos. I hope I got that name right. He's a professor of the Department of Mining and Materials Engineering at McGill University. He holds a Canada Research Tier 1 in Sustainable Mineral Resource Development and Optimization under Uncertainty and is Director of Cosmo Stochastic Mine Planning Laboratory. Roussos holds a PhD from École Polytechnique de Montréal and MSc from the University of Alberta in Edmonton. He works on stochastic simulation optimization, as well as artificial intelligence applications in mine planning and production scheduling, along with the simultaneous optimization of industrial mining complexes and mineral value chains under uncertainty. He has published extensively, maintaining large competitive grants from the National Science and Engineering Research Council of Canada, and a long-standing partnership with Anglo Gold Ashanti BHP, Agnico Eagle, Anglo America DBS, IAM Gold, Kinross Gold, Newmont, and Vale, who supports his research. He has taught and worked in Australia, particularly at the SMI, I think, in the past, North America, South America, Europe, Middle East, South Africa, and Japan. Today, Roussos is going to talk to us about simultaneous stochastic optimization of mining complexes, a paradigm shift, development, and challenges. Please join me in welcoming Roussos. All good to go?
Thank you, Eric, for the introductions. I'm sorry I was a bit slow in connecting today, but we should be okay, I hope. So we would like to see what we call simultaneous optimization of mining complexes. And first of all, what does that mean and what it is? And you will see from there why we have this comment, a paradigm shift, and developers and challenges. Let's start from somewhere. Well, how do we typically work? Someone is trained in mine planning and does production planning in the mine site. People look after processing plants and the different background in their training and their work. Also different people who look at the markets and what do we sell and what process to use. And of course, how do we deal with waste and reclamation and tailings and so on and so forth. In looking at all this, the one question that has been coming up for decades is why do projects fail? You see one here at the bottom, done in Australia long ago in the late 90s, that says 80% of failures are due to geological risk. This geological risk, as it's called here, it's nothing but our understanding and description and figuring out what exactly is in the ground. And while I use this example here, there is a similar study published in Canada from a colleague at the time around the year 2000, who says exactly the same thing, even worse than what this report says. And over decades, we have says again, it's our understanding and how do we manage these things in the uncertainty, so to speak, in the what's in the ground. And of course, we see many more studies on that over the years. So at some point, well, when we see this kind of issues, the question comes up, how can I do things differently that may be better and allow me to address these issues of what's in the ground, how do I manage with what I know and what I don't know in order to end up producing the metals that we are interested in. Yeah, I'm sure that all of you know these things. This is how do we represent a mineral deposit in the ground with what you see here, the blocks. And the block sizes are essentially the selectivity we have in extracting materials. And what do you do where you see, say, the question mark in the block? You see, well, first of all, long-term mine planning or strategic planning, another word for the same thing, is when exactly to extract every block. So what is my yearly plan and which blocks I should be extracting a given year and the next and the next. And then, of course, you extract, but then the question comes, which destination should we send them the materials to? So you have several ones here. And then you say, how do I decide these things? Well, I better know better or describe properties of the block that I consider. And of course, it's the grade of whatever the grade is, but there's typically several other parameters that are also of interest. In other words, the quality of ore or the characteristic, the geochemistry of the ore and this and that and that I need somehow to consider in order to figure out not only when to mine it, but what the destinations are. What do we do normally for decades and decades, starting with Jeff Whittle back in the 80s or even before? So we end up saying, okay, I will find a model of the blocks of what is in the ground. I will put it in an optimization process. In the older days would be less Grossman and stuff like that. Nowadays, more efficient and better algorithms, perhaps. And we produce out of these different forecasts, like, for example, we care, of course, about cash flows per year, and you see the graph that you have here. So what do we typically do? We try to find an answer that is as close as possible to reality. But then there is another question. Is that the only way I should work? And if there's issues of, for example, it's not the only source of uncertainty, but let's start, what's in the ground? What is my understanding of what's in the ground? And how do I use the information that I have? Is a good question that says, well, uncertainty, maybe the forecast that I do should not be single values. This is one value, I do my best to get closer to reality, but the range of possible values, like the kind of histograms, whatever you see here in the bottom right side, and while hopefully within the range of values we report, there is the real value. And of course, I can tell you plenty of stories if you want about this kind of issues, like people in the petroleum world don't do this kind of give me a value and better be good, but they will report typically what is called P10, P50, P90, the probability of 10%, 50%, 90% of what I'm forecasting. Is it cash flows? Is it amount of metal, etc., etc. What is an interesting observation to bring up is that if we start from somewhere, let's say the models that we do for what is in the ground, we know for decades and people have worked on better estimation methods of what the model in the ground. But suddenly if you start thinking about it, you realize that all these methods, even whatever we may consider the best method, is the one that gives you the best average value of a block, of the grade of a block, not the possibility of being higher or being lower. In other words, the representations we use are representing a deposit with average values for block, which leads into what you will see shortly as an effect of smoothing of reality. So you don't necessarily see that much the higher values properly, or you don't see the lower values properly because all the values we interpolate are an average value. There is an example for you a long time ago at Superpit, and this is a very, very small part in the middle where there is a load or whatever, and you see grades simulated in the block models the mine is using, and you see three scenarios, and you see on the, I don't know if you can see my pointer, but you can see in the bottom of the first one, it's all high values, red color. You go to the middle example, the middle model, and you see low values. You go to the third one, well, mixture of different things. If you work in mine planning and I tell you, oh, this is these three examples, you will probably say right away, well, I see differences and maybe my mine plans will be different if the deposit is the first or the second or the third or any other one. These models that you see here come from a different way, not a new idea, but come from the idea of what we call Monte Carlo type simulation of what's in the ground. Nothing new on the concept. We have seen textbooks and stuff in the 70s that describe the early days of the methods like that. But what you see here is three scenarios that we can call them equally likely, for whatever reason, equally likely to represent reality. And another thing to keep in mind that the number of blocks we may want to consider is quite high. The numbers you see here is from the Superbit at that point in time. So what is the story with that I brought up, estimation, simulation, and stuff like that? Let's take it's a real deposit in South America. It's a bench in a gold mine. And you see on the left, you see the locations of the available diamond drill holes. Black is higher value, the less dark it is less and less and less. And in the middle, you see, okay, let's take now a couple of the estimation methods we use and estimate the blocks that the mine is going to mine, to extract. and you see that what we see in the middle. And at some point, someone is going to say, but, well, it's an operating place. So eventually you realize that they will go on the bench, they will do blast hole drilling, they will collect samples, and then they keep doing things from there. So suddenly we take the blast hole data that we have from the same bench, and we say now if this is the size of the blocks that I have, I take the estimated grades or the grades from the sampling that I have per block. I will average them up, and I will give you a value per block from the blast hole data, and you can guess that this is probably the best I can go close to reality for the blocks that I have here. But look at what you see on the right-hand side of this image. You see blast hole data and the actual values for the blocks that I have previously estimated, and you see they look very, very different from the estimated blocks, independently of the method that I use. And you scratch your head and you say, oh, why is that happening? Well, you realize then that what I do in the normal estimation methods, all of them, I find some average value, which means the model that then I use to work with and do the rest, well, does not represent the variability that you really have in the deposit that you are working with. And the smoothness that you see here also has another effect, high-end and low-end proportions. Well, you won't see what is in the ground. So this is now to look at comparisons. We have now in this slide on the left-hand side, you have the actual blast holes that previously we saw them averaged over the blocks sizes they had. These are the actual values, very closely spaced as we expect from blast holes. And then you say now, okay, what do I do? I take the exploration drill holes that I have, right-hand side of the figure, and I use these simulation methods, as we call them, to find the values at the same location or all the locations I want to model, as you have them for the blast hole data. And what do you see here? You see now that, well, the variability that we see in the blast hole data more or less exists in what you have. They're not the same by any means, because they're based on, I don't know, 25, 30 drill holes, as opposed to directly the blast hole measurements. And you say now, okay, but it looks more realistic. And going to the same kind of a concept that I mentioned earlier, you have multiple scenarios, equally likely scenarios, as we call them. You find another one, a second one, and you see that also it's not the same as the previous one, but it reproduces the information that's available in the data. And generally, it looks more variable and more realistic in a sense when you compare it to what I get from the blast hole data. And of course, then you say, when you look at these things, you say, okay, great, I understand. The simulation gives you a more realistic representation of the reality. But the fact that I can generate the equally likely models, one after the other, and as many as you want, are telling me, well, how do I deal with that? Because we're used to work with a straightforward, take a model, put it in the optimization process, give me the long-term plan. So what you see here now is, however, if you look at it, you will probably start realizing that simulated scenarios are different. They're equally likely, but different. In other words, a group of them will probably give me a better understanding of what the possibilities are. In other words, you can see it as a way to quantify uncertainty by using a group of simulations to do what we want to do next. So there are two things that the summary of this quickly to put up here. The one is that the models that we have seen, the simulated models, reproduce the spatial variability of whatever we look at. There is no smoothing, there is no nothing. There is production of anything that is in the available data. Number one, and while at the beginning we say, okay, what do I do now? Because they're all equally likely, what do I do? Well, the answer becomes that yes, they're equally likely, so use them to quantify the uncertainty of what exactly is in the ground in terms of properties, from grades to geochemistry to anything else that is relevant. A very old example that you see here in a mine, it's a gold mine in northern Queensland. You see on the top left section, it's three years of mining, the three different colors telling you year 1, year 2, year 3. And then you say, oh, I have them. And it has been done properly, but the conventional estimate, Woodle for X was at the time the common industry standard. So you get for that a concept that gives, in terms of community cash flows, that you see the red lines, the red dots that you see in the graph. And then someone says, that's actually a real story, that someone says, well, if I can simulate and simulate, what will I get? And what will I get means now, if I follow the plan that I've generated, and scenario one of the simulations is what's in the ground, what will I get? And then you repeat that for different scenarios, and you see here for several of them, you see the gray lines, and you see that the gray lines is not particularly close to the red dots that you have from the conventional work. In other words, this is telling you that if you follow the plan that you have, your performance isn't going to be the red line, the red dots that you have here up to the life of mine, but it will most likely be maybe not too bad at the beginning, but as you move forward, the differences will be very high, and the average value from the gray lines will be, I don't know, 20% or more out of what you have. And you start asking this kind of questions, and maybe I should say that, well, of course, you see these kind of things. If you start thinking afterwards why this is happening, if you look at the details, you say, well, if I estimate, I smooth out the high end and the low end, and depending on where my cutoff is, well, I will miscalculate what's happening. Is that new? No, it isn't. In fact, we learned that from the petroleum industry, and you go back to the 80s and things like that. And what you see here, and I have these examples and the dates, 1990, 1992, and I don't know, Chevron, etc. What you see here, what we saw in the couple of decades later in mining, the black line that you have in both ones here is the one they done by having a single value for porosity permeability situations, whatever the values they care about. And then you simulate all these properties and you run the reservoir flow simulator and you get these forecasts. The interesting, the petroleum does that forever, I would say. The point, however, is that the reality for mining is a bit harder because of the following reason. If you are in petroleum and you dig a well, petroleum and whatever else, maybe water, maybe some gas will come out. You care what will come out. You don't care about which path the materials follows in the underground to come up from the well that you drill. In other words, can be any path. As long as I know I can forecast what will come out, I'm happy, and therefore the graphs that you see here quantify uncertainty in production. Well, mining is a little bit more complex because, well, I do care what I will mine when, and it's not that it will come out, materials comes out from a well or anything like that. We need to go mining and extract the materials from the ground, and we need to know exactly which parts to mine when, etc., etc. That's exactly one of the reasons that makes the use of these approaches harder for mining. So what do we see in this kind of conventional way? Well, suddenly we are going to say we will change a little bit the way we work, and we start realizing a few things if we want to do that. You see here that you see a few points, but the more main ones is what you see, non-linear transformations. Why do we think that the relations we have are linear? Meaning averaging the optimization process will not necessarily give you an average output if what you do is not exactly a linear operation or function. In other words, the average value of a block and the average out isn't going to happen. The forecast that we do for the conventional mine planning don't necessarily represent an average value based on the input we use. That then becomes quite a bit of a problem in addition to, okay, why smooth scenarios and how do we link the various parts, etc., etc., etc. If you wonder why this statement, there is a very, very simple example. There is a block, let's say copper, the value is 0.11, whatever it is, and how do we work in the conventional way? This is the average value, the estimated value. We plug in to find the economic value of the block. That's what we do conventionally to say dollar values per block, what I extract when. So what do you do here? You have the copper price, or whatever recovery and all the values that you need, and you plug in the value of the 0.118 and say, okay, now that will give me the economic value of the block. If for the case where example I consider here, you do that, the economic value would be very negative. So that instantly is telling you this is a waste block. Okay, then someone would say, fine, but what are for reasons of providing explanations and why do we say averages or not averages? Well, there you go. Someone says this 0.118 comes if I have 5 possible scenarios, 0, 0, 0, 0, and 0.59. So what happens then? And someone says, okay, don't take the average value and work with it for what we do here in economic values for blocks. Take each one of them, plug the value in the formula, and see what values you get. So the red values and negative are telling you waste, 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 and waste. But there is a case, the last one, that says, oh, it's or. If you take now the average here of what is the value of this block, you will find out that the value becomes positive. And you may say now, it was something that before we thought it was waste. If we've averaged the values here, well, it's OR. Or maybe you would say it's OR, but 1 out of 5, or a 20% chance of being OR. Nevertheless, what you see here is that the conventional optimization might be very complex and very many good things about it. But if the input is an average value, why do we expect that the output that we'll get will be an average forecast? And if we think that way, there is a long list of issues. For example, why do we think that the conventional output is optimal? Yeah, the process is optimization, the mathematical programming, we understand all those things, but the inputs are what matters and leads us to what we get, independently of the good parts of the optimization process that we use. So if this is the case that we see, start asking questions. I would start asking questions right away. So why do we think that the long-term plans we use will materialize? Why do we think that exactly what we think will mine per year will happen? If it's not exactly, if it's generated the way we're talking about. So again and again, why do we think this is a better assessment? So why should we put all our efforts in an average dollar value that may not be the better one or whatever, the optimal one, and so on and so forth. So what is the answer to these issues? Well, the answer is very straightforward. If you work with a conventional way, one way to explain the concept is this typical integer programming. I have these 4 blocks. I have economic values for blocks. So what do we do in mathematical programming? We have an objective function. For us, maximize dollar values. The optimization process will tell us the C's and the X's. The X's is a binary variable, 0, 1. If the optimization process tells you is 1, it's OR. The block is classified as all these blocks C1. If it's 0, it's not considered, and it keeps doing that in order to its waste, and so on and so forth. And of course, there are constraints, so all sorts of constraints. For example, if an open pit, this is an open pit, if you don't mine the top blocks, how can you mine the bottom block? And a long list of constraints. And having said all that we said earlier, well, this is now a reasonable answer to all this. It's called stochastic mathematical programming or stochastic integer programming. It exists in textbooks since the late 90s, or at least this is where I started looking at these things in the concept of stochastic optimization. What do? Well, they will take all the models that we have, all the simulated scenarios that have been generated, and they will maximize value. But as you can see in the equations quickly, the S and the X is, well, this is the value of the block, but not only one value, they're all the values of all the scenarios for all blocks. In other words, I have a process that optimizes given that the values that it considers are not constant or the average grade of the block, but they're variables. And there you go, if you go this way, and quite some time ago, we developed you rewrite the optimization process. As you can see an example here, have multiple inputs, different scenarios. It takes them, it will output a single optimized mine plan. The colors are years, and will give you a forecast. But the interesting part with the forecast is that you don't have one value. You have, if you have uncertainty in the supply, quantify and say, well, this is the P50 or the average type forecast, but the P90 and the P10 on how chances of being higher and chances of being lower in the forecast that we have. So in other words, you will also find out that these MPV qualifications are typically higher than the forecast we do with conventional methods. But we'll get to that shortly. There is an example to when you see these things. You have on the left 2 schedules in a section. The first one uses an outline. The optimal pit is not optimal pit, but the pit limit is the optimal one in the conventional way. In the second one, you see in the bottom is again stochastic mine planning, but we allow the process to decide when to stop mining. And you see suddenly that the materials that you extract are more because the pit becomes bigger. And then if you look into the graph that you have here, the cumulative NPV and production years, what do you see? The blue line in the bottom is the well done but conventional model and optimization of this in this case. And on the top, you see two lines. The red one is the one that says allow the process to the stochastic optimizer to decide what the pit limits are, make money at on stop. And you suddenly see that you have massive differences between the work with the schedules being stochastic versus the deterministic conventional schedules that we have. And the middle line that you see here is nothing else but the old pit limits, the conventional pit limits that we see in the top left graph. So we see all these things for quite several years now, just about every other case study that exists. So we find out that, first of all, if we go along this forward with these concepts, we have lower risk in what we mine. We typically find higher values, and of course, higher value reflects the fact that there is more metals or better production of whatever we extract. And suddenly we say, okay, find the concepts, but why anything in a single mine is optimal? If I consider it independently of, let's say, another deposit in the same area that feeds the same processing plant, or independently of how the mill is utilized, or what's in the market and uncertainties when there, or rehabilitation and everything else. So the key concept that comes up, if we think that way, no, this is not a new concept. I learned that in working for Newman in Denver in the mid-90s, is the idea that try to optimize things with one optimizer, because this allows you to have interactions between all the components that truly will better provide an optimal answer, as opposed to I do things separately from one from the next. And well, there is your mining concept now, the mining complex. We see it as an integrated business, and it has, okay, in the little example here, there's 3 mines, but suddenly you see waste dumps, you will see tailings, you will see, I don't know, smelters and refineries and cantonments and ports and all these kind of things, until we go to the place where we produce metal and we have it in the market, and we consider the economic values there, not at the beginning. And if I have different scenarios in this kind of optimization methods that take all the components and say, well, I have my scenarios here in terms of uncertainty, grades, and properties of blocks, well, I can trace the uncertainty from the start to the end. And when I get here and put things in the market, I have an uncertainty of how much will I be able to put in the market, like the P10, the P50, and the P9. And don't think that this is the only thing you can do here. Suddenly, if you want to say uncertainty in the markets, why shouldn't we combine here not only the uncertainty for the supply, the mines, but the uncertainty for the markets? But we do that at the end of this process, at this mining complex, and where we produce things. There's no longer economic values of the blocks, because economic values of the blocks kind of generate limits in how we can consider things. We look at dollar values for blocks. What if I blend them? And the chemistry tells me that what you will get is something very different, for example. Not the time for me to explain to you the math and all this kind of stuff, but let me show you the objective function in optimizing and mining complex and convey to you what the components do. The very first one that you see here, first of all, you see 1 over S in these components. That means I consider all the scenarios that I have. There can be scenarios only from the uncertainty in the materials in the ground, or combination of them with the uncertainty in the markets, if I want to do that. The first term, so here it says the attributes of interest, but what does it do? It tells us what exactly is the money I can make minus the cost of generating the products. The second component is you see a minus here and you see different things. Well, what does it do? Typically, we have a long list of different kind of restrictions in different cases. Maybe there's a mine that needs to have, let's say, I don't know, silica to magnesium ratio within the limit. Or maybe we have some reason to say we want to send to this destination this range of values, or for ore or other types of materials, or anything you can think of. So what does this term do? It says give me the limits that you have, what you want to produce, and try, by looking at different scenarios, the simulations that we have, how to combine the blocks that we are mining to minimize the deviations from the targets that we have. And it does it, however, in a different way than the flat penalty. It says, okay, upper or lower or whatever, there is a penalty, the C that we see here. And what do we do there? Because we want to make sure that we, as much as possible, we force the process optimization process to minimize deviations from the first year rather than bet more than the second, and the second more than the third, and so on. This component means now that the penalties we put here, we discount them like we do with other things. So the value becomes, if you say the value is 10, well, the 10% discount will give it 9 for year 2 and less and less and less for the years that follow. This is exactly that. And of course, there is CAPEX and investments, but we can't say everything on the list for one seminar. So what does this term does? It tells me now what conditions do you have in meeting the tons you have to the processing plant or the silicon magnesium ratio, if that's what you're interested in. And we like these approaches not for any other reason, but the optimization process looks now directly on the products and what stands behind them, meaning processing stream 1 that you have here, well, the metal tons and stuff like that, but also issues of throughput or recoveries. Well, the recoveries are not necessarily, they're not linear, as we said earlier, and the throughputs and stuff like that. So this ability allows this way of looking at things allows the optimization process to look directly on a given processing stream, what the combination of the blocks and their properties do, and therefore decide what is the best or the optimal thing to do. And you probably see a lot of things in the comments that you have on the side. One thing that comes out of that, okay, you may say, great, okay, fine, interesting, but if you had asked me, for example, a decade ago, I would say, yeah, interesting concept, but good luck. The same way that the implementation of these typical concepts in the past, well, making too many assumptions. But nowadays, this is the interesting part. Here, there is an example for you. Let's say this mining complex has 3 mines. And you look at the bottom, you will see 18-something million decision variables. Well, you realize when you see that and you are familiar with operations research methods, well, good luck in solving this kind of problems with the solvers, the typical solvers that we have. And if you have, let's say, 1,000 decision variables, we have problems. So the interesting part here is that we look into what we call solvers, and therefore you go into what's called the heuristics and things like that. And this is an area nowadays that there is, in addition to the various heuristics we have, we find a learning mechanism from type of machine learning or reinforcement learning that allows us to improve this kind of solvers. And yes, we can get block by block schedules for extremely large problems. There is an example for us. The operating gold mine complex that you see here, the typical one is in Nevada, gold mine in Nevada. What do I have here? Well, it has two pits that we extract materials. It has a lot of stockpiles that they use as they work. They've been producing here for 15 years, huge amounts of stockpiles. In addition to that, the autoclave, for example, gets materials from an underground mines close to this area. And again, other sources like Newmont was the owner of this mine at the time. They would send materials from the other mines in the area. They would send it to be processed here. So you realize that I have plenty of components here, the autoclaves, the leach and the mill and anything else, and stockpiles all over the place. And so, okay, that's my mining complex. How can I deal with that? Well, first of all, you maybe know or maybe recall that this kind of deposits have, as you saw the example at the very beginning, multiple properties that we need to simulate, properties in the ground for blocks, from gold that makes money, or sulfur and oxides and organic carbon and whatever it is. So we have to simulate all these properties that are relevant to what we want to do for both mines. The second part is, well, we have stockpiles. Typically, we think we know what's in them, and we eventually sometimes realize that's not true. So the company here operating the mine samples the stockpiles they have. You see here an example. This is now from the samples they collect. It's the same section in one stockpile. to tell you now these are three scenarios, same story as we do with the deposits and the properties in the ground. Well, same thing for the stockpiles that you see here. And you see how different these scenarios look like. Plus, you start understanding that there's materials in the stockpiles that you think are not there and all this kind of stuff. And of course, you can also calculate the other sources we have here. For example, it's materials from previous mines. They have a good record of the previous, let's say, 15 years of what exactly we're expecting to get and what they got from the other mines. So this allows us then to see what is the differences and then simulate the scenarios of how this may happen in the future. So there we go now. What this process of the optimization will give us, more or less along the lines of the objective functions earlier. And the interesting part is what you see on the top colors. This is the stochastic mine plan. And if you take two benches, bench A and B, well, the colors are the years. Then you say take what is the corresponding mine plan from this one of the two deposits to for the mines mine planning, which in itself was very, very advanced, I would say, but the conventional deterministic thinking. So look at the colors. Well, bench A and B, they have very, very different years that the benches will be mined if you're looking at the stochastic mine plan versus the conventional one. So keep that in mind, and it's an important part because if I start doing something in reality, it doesn't mean that tomorrow morning I can go mine different things on Saturday, etc. And then, of course, you will ask, fine, I understand the practical aspects that come out of this. The second one is going to be now, okay, do I make more money or do I produce more? So this is now what the expected performance of the red lines of the conventional way of doing things. And whatever you assess risk and stuff like that will I get, while there is the NPV, it's 14 in the six following years is, I don't know, 14% higher. And of course, that also corresponds to 11% more metal. But in this kind of cases, the 14%, we're talking about tens of millions, or if not more. So these are not exactly small numbers if you look at what these things are. And there are also other things. This graph is what they call acid consumption in the process of materials they use. Nevada has limits on what they can use, the amount of acid per year or month or whatever it is. So that's the green line that you see there. If you follow the mine's plan and if you test it, will I get what I expect by having scenarios? You will see the red line. But if you test the stochastic plan, how it will perform, you see that for whatever we see here, the chances of staying within the limits are way, way better. And the other story here is, well, we did that when that was, I don't know, the 13th year of mining. And if you have done this from the beginning, you will get bigger pits and more life of assets and stuff like that. So you ask the very obvious question, and like everybody else, from me and everybody else, okay, fine, we see models. Models are models. What is now the reality, the models versus reality? This is a couple of graphs you have here for a very large copper deposit an area somewhere on the planet. I cannot tell you the details, but this is what you see. The top left graph says tonnage above cutoff grade and cutoffs on the other axis. And you have different colors, different lines. What is the red? The red is giving you what is the ton above the cutoffs that for different grades. And but this is now from the conventional forecast the mine did on the 13 years they have been mining, or 12, whatever it is. And then you say, okay, if I have all the information of the past, can I use these technologies, do again the same forecast with the same data? But now, if I've been mining for 13 years and I have the data there, can I compare what the stochastic framework gives me? The stochastic framework is the black line, the P10 and P90 dashed ones. Well, what do I get if I do comparison with the blast hole data that I collected while I was mining? And suddenly you see now that, which is now the blue line, and you see very clearly that the blue line is surprisingly close to what the stochastic forecast has given us. And you will see that also in the grade above cutoffs and other graphs that we have, and many other graphs that I cannot show you. You will see on the top right, of course, every time we see differences, the mine plans are different, and that's something we need to remember. But the process here makes a point that, well, there are reasons why, obviously, if we're more realistically representing what we have and what we deal with it, not surprising that The example that you see here looks extremely well. I don't know. When we first did that, the company did that, and I saw the data. I told them it's too good to be true, and we made them redo and evaluate everything to go back to the results that you see here. So this is now a framework that seems of interest and so on. Can it be more complex? It can be way more complex than what I showed you. There is an example that says, how do I optimize the use of the processing streams that I have? And it's not necessarily feed the processing streams all the time, the maximum amount of materials you get through. Or you can say supply and demand, and that's what you see here in one of the graphs for this kind of cases, like cash flows versus periods. And you see the black line is the only supply uncertainty, and the green is demand, meaning market value, simulated scenarios for the markets. And of course, many things that one can do. One thing that we've been doing lately more than the last 2 years, more than before, is integrate components that have to do with waste management and progressive reclamation, which means add components into the objective function we saw earlier and try to integrate reclamation that we do in a more consistent way while we are extracting materials from the ground and looking at the properties of the materials we put into the various places. Okay, you say, okay, that's fine, and you can have your questions that typically we all have when we see these kind of things or new things. But all these things that I showed you have been 2-3 years now. They're commercialized, and they're software people can find in the industry and use them, etc. So from a research point of view, what is that is of interest and where to from here? So I think you will find this part interesting, or at least we find it very interesting. We call it the self-learning mining complex. So what is this story? Well, you realize, we all know that if we are in an operation, you have, nowadays we have sensors everywhere, where we have tracks, where they are, how they are moving around, etc., etc. We have crushers, what material is goes to the crushers, what happens there, shovels, where do we put them, when do we move, and what we do, conveyor belts, and anything else you can imagine. And of course, the most conventional, more conventional existing things, okay, blast hole data versus doing models only with exploration drill holes and stuff like that. What comes from here? Well, if we stay with the story of a mining complex, there is one for you. You will see that you have 2 mines, you have plenty of crushers, you have 3 mills, and 2 kind of different products that you have, copper and cathodes, copper for cathodes. So the idea then becomes now, as this existing mining complex operates, we collect information, and we have unbelievable volumes of material, of information we store somewhere, and we don't necessarily always know what to do with that. But you realize now that if we operate, there is a list of new information, like the materials extracted, how do the what exactly is really being loaded, where it's going to send, how things perform, and anything else that you want. So you can see all these things as you operate and you collect the information. So the idea now is that if I do my operation in an operational case, it's not strategic planning anymore, so short-term planning, if you want to call it that way. So what happens there? I operate, and if I collect all this information, that somehow I use them, well, suddenly we say, fine, you have production now, you see grades, well, how about updating the simulations of the deposits that you have generated and you do your work with? But then you will also say that in short-term planning, well, we do care about what happens with the shovels and the cracks and the processing plants and their performance, and are they always doing the same thing? No, are they having plus and minuses? So all the uncertainties with the performance of all the parts that we have here will be then updated from the information we collect. And if we update them, then we suddenly are going to say, yes, take the updated models and assess your short-term plans. What do you mine the next few days or next week, and so on and so forth. And then take all these updates back to your mining complex and keep working. So you see the typical buzzwords we nowadays use, like big data, of course. You can see that from sensors and all these kind of things. You have machine learning and different methods around this from that new developments in that area. And of course, then to use this to adapt to the incoming information from the short-term things. In other words, this is what we saw as a self-learning, and probably you will see that a little bit better as I keep going. You realize that I can do this. I collect data, top left, big data or whatever the buzzwords we use are. But what do? I update the simulation models that I have. But in the short term, if I have some quantification of uncertainty that comes with crashers or shovels or trucks or anything, I can update these things too. And as I update these things, I can start saying now AI, meaning now I will use some of what is called reinforcement learning to provide adaptation in a sense of what do I mine the next day or the next 2 weeks and so on and so forth. So let's see now what happens if we do this kind of work. I will not describe the details of this, but this is now instead of the conventional method for like Kalman filter that people will use to update whatever spatial models we use in other industries or whatever. Here we go to what you see as active picking reinforcement learning, and we update what is in the ground. Why do we do this? Because it seems to be performing this approach better than the conventional models. But it's not only updating the deposit, it is deciding what to do in what I mine next, and I have to figure out how to adapt the processes. But suddenly you see here an example, I mine 2 fronts of the deposit. I have, let's say, 3 blocks. I look at the middle one and three blocks to decide what to do and where to send them, combination 9 decisions. If you take the other front, again, 3 blocks and 3 destinations, 9 decisions, the combination is 81. So if you start saying, I extract this block, I tested where to send it, you find out as you move forward from one group of blocks to the next, the combinations increase exponentially. So suddenly we need to figure out how to deal with these things. And in other words, a very complex process. Some time ago, we looked at, over a decade ago, we looked at what DeepMind developed and published. It's published work in which they give you the method that of playing chess and winning against the best, the artificial intelligence wins against the best chess player. The difficulty, so it's interesting to understand the models there and see if we can use them for what we do. We simply find out that the decisions there is what you win or you lose, and that's it. In our case, I was trying to bring up the massive number of decisions that need to be made, and the short answer is, well, good luck if you think that whatever you see in DeepMind and their algorithm in what you do, you end up rewriting things to accommodate what you have. The method they use is what is called the decision trees that you see here. It says, where do I go? What happens when? And at the same time, they combine that with some forms of reinforcement learning to figure out is improving the values and so on and so forth. But this is published work, and if anybody has an interest, I can certainly send them to you. What is more interesting for me to see besides the ideas on the basic methods is what happens here if we are in our mining complex, the one we started with. 13 weeks of production that we are considering. So we have supply of materials and equipment uncertainty, and that's the 2 components we will consider. And it's a complex case. There is a copper mine, but there's also arsenic and other things that we need to worry about. And so let's see now what do we get. It's interesting now because what you will see here is the following. On the left, it's the stochastic framework and everything else, and uncertainties in different parts from equipment to grades, but standard way. And that's what we say now. We collect the information and we update what's in the ground. In arsenic, if that's one of the models, you see suddenly that definitely the top on the left and the right very different in the variability and the number and the colors that you see, meaning the ranges in grades. And then if you look at the extraction sequence, look at the 2 examples, the initial and then the updated one, you see that you are the different colors are weeks. And you see now the colors have been changing, like the light green that you see here doesn't exist before in the initial one. In other words, we have an adaptation of the sequence of extraction per week with the 13 weeks we do, given the new information that comes in and our updates of what we have. And the updates I was saying earlier are happening through this machine learning, reinforcement learning methods. And of course, you will ask, okay, I can see the differences. Does it matter? Well, suddenly you're going to find out that we're talking now for 13 weeks. So suddenly you have about 13% more higher value on dollars just for 13 weeks, which is not a small difference. And if you go say, okay, how about the copper production? You find out that you have significant increase if you now follow the updated plan versus the old one. So these things do make a difference. And if you want also, you can add the issues on allocating and dispatching trunks along with the optimization of the sequence of extraction. And for, I don't know, 5 days, you see some differences here, etc., etc. So this is interesting because suddenly we are moving forward in what we call the self-learning mining complex. The term comes from the idea that we collect data, we update, but the interesting part on these methods, from reinforcement learning or whatever it is, all the machine learning methods, allows the system to learn from what is happening. And this is the level of learning, meaning what do I see in the sensors and everything I collect? This is the learning that I get from there to then apply and do better. And okay, we are a bit longer than I thought we would be. And of course, thank you to the various mining companies that support the work that we do. And that's it. We cannot hear you.
Thank you very much, Roussos. We have about 5 minutes for some questions. Those online, can you please post yours into the Q&A section?
Thank you, Roussos. That was fascinating. My name's Tom Evans. I'm an exploration geologist originally, but question, with the stochastic resource models, have you tried looking at how you can take a conventional resource model for that same deposit and modify the inputs to that conventional resource, whether it's the, the Kriging parameters, so it converges with the stochastic P50 model to kind of get an insight into what errors
no,
in
not really.
selection?
I don't think you can do that unless you have simulations. And if you have simulations, the answer is fine. Well, if I have them, why shouldn't I use them? In
Yeah,
fact,
no,
what we see, but what you see also in this area of reserve reporting and calculations, well, you will get different answers if you get simulations versus Kriging, even if you fix the P50. Because what we see in this kind of cases is the averaging doesn't give me average out. I don't know how to exactly fix the input. Because if it's one value, the system doesn't see how things can be changing. And that's the key difference there.
Cool. Interesting. Yeah, I just think it would be interesting from a conventional resource modeler's point of view to sort of get an insight into why they had, or how they had come to arrive at Kriging values that were, were not estimating the model, estimating the resources accurately as it could be.
And you look, but you need to see that when I do something like that, I give an average value for this and that our reporting is average values, right? So what you're saying is, can I essentially adjust my reporting by playing with Kriging or doing something to be closer to what I would get from simulations, if I understand correctly? And
Yes, that's correct. Yep.
For all I have known, I don't think that this is feasible in a realistic way.
Cool. Thank you.
Do you have any more? Okay. Thank you, everyone. I think that's all we have for today. And next week, hope to see we have Professor James Wong from the School of Chemical Engineering talk to us about hydrometallurgical process commercialization. And thanks for coming, Roussos. Thank you.
Thanks for listening.
Bye.
Thanks for having me.
Bye.